Hello, everybody. Good to see you again. Just a second. I'm just going to join the Zoom over here on the computer at the same time. Great. Looks like we're here. That's strange. So my Zoom is behaving a little bit oddly right now, in the sense that usually I can see everybody. One moment, please. Are people able to see me on this YouTube live? If you are, please type into the chat because then I can see that. Oh, there we go. I don't know who did that, but whoever did that, thank you. Now I can actually see everybody. So that's good. Yes, into the chat. Great. We're not going to use the chat. We're just going to do it the way we've always been doing. And let's turn this into full screen and get rid of that chat. So now I can see everybody, which is awesome. Also, I'm trying to see where I'm standing. So this looks pretty good. Okay, so we're back. I think we're back here. If people are able to get this audio signal, could you please do a thumbs up or like wave your hands or something if your camera happens to be open, because then I will be able to know that we have the connection through. Okay, we are through. Solid. Okay, great. Well, it's good to see everyone again. I guess it's another week, another very busy week. I guess I say the word busy because, as some of you may know, I've actually been working on some coronavirus-related things. So, in fact, I was up until 5 o'clock last night. I have turned into an Android app developer too. It's pretty cool. The last time I ever did computer programming for real was with like simpler stuff. But anyway, today we're going to talk about just pure mathematics because that's also kind of fun. I want to continue from where we left off last time, and we left off with some kinds of formulas. And just to say specifically where these things came from, these were because we were trying to figure out under what conditions could you find that a relatively sparse graph with tons and tons of vertices could be embedded in some kind of a regularity diagram. And in this regularity diagram, I have some blobs. The blobs are of size m. And I also have that somehow between each pair of those blobs, I'm both epsilon regular and density at least delta. So that's why there was a delta floating around. And the procedure for embedding was just being clever and not trying to say that I need every vertex I put here to be possibly adjacent to every other vertex I've ever embedded. And as we did all of this analysis very carefully last time, we came down to find out that we just need two things to be true in order for us to find a quite large object inside. One of the things is that we need to know that as our parts as our areas we're narrowing down on get smaller and smaller, then at least the delta minus epsilon to the power capital delta, which is how small this thing gets, is at least epsilon fraction of the whole thing. For today, I want to think about a specific application where the little delta is going to be 1/2. So today, we're going to do a really, really, really nifty proof. And inside this really nifty proof, we will be using the situation where delta is equal to 1/2. And I wanted to look at this delta equals 1/2 superimposed on our inequalities from before, because I want to see how that affects your choice of epsilon and capital delta, your choice of epsilon. Also, another thing to think about in all of today's lecture, capital delta is going to be a constant. I don't know, maybe it's 5 or something, but it's just going to be that there will be some number, capital delta, and we're just going to be trying to prove statements where the capital delta is given up front. So think of this delta as something like 5, just for the sake of it, okay? So delta, capital delta, is going to be some number like 5. And that number can be changed. It will be just any constant that we want to put in front. Now, if I have that down, look at the first condition. The first condition is then telling you some condition about epsilon in terms of this capital delta, in the sense that as long as the epsilon is smaller than something, some number, I'll be good to go. So the important thing here to notice is that whatever the capital delta was, that gives you a condition on epsilon. Remember, the little delta is 1/2. So since little epsilon is going to probably be quite small, as long as little epsilon is quite small, then this is basically like close to 0.4 or something, or half to the power capital delta. And so what you're seeing from this, hopefully, is that whatever the delta is, whatever the choice of that capital delta is, that will give me a condition on epsilon, where any epsilon less than, let's even do it like specifically for this example, what would work? I'm saying, like, suppose I delta equals 5, if big delta equals 5. If big delta was 5, then if I had 1/2 for the little delta, this 1/2 to the power 5 is like 1 over 32. So it looks like if I chose epsilon, any epsilon less than 1 over 100 works. And when I say works, let me stand here. When I say works, my works is works for this particular inequality. I don't yet know about the second one, but at least I can make it work for the first one by choosing the capital. I mean, if not by choosing, if the capital delta was 5, then I could choose the little epsilon to be 1 over 100. Because if you look at what happens here, the little delta is a half. Half minus 1 over 100, or even less than 1 over 100, is like at least like 0.49. And something which is at least 0.49 to the power 5 is certainly bigger equal than 1 over 100. Are people following this? I'm just trying to show the flow of how you would argue through what we're about to do. What we're about to do is we will have a very specific situation where little delta is 1/2, and I'll be able to use that for sure. The capital delta will be an interesting parameter that's fed into the theorem we're about to prove. But that parameter, capital delta, will determine what epsilon range is okay. How about the second thing? If we look at the second thing, how can we get the second one to work? Actually, when I look at the screen in front of me, which is how I'm looking at what I'm pointing at, my vision is not very good. So you'll sometimes see me looking down here because I have another copy of the screen here. In some sense, I'm doing like an eye test every single time I teach this class. But let's see what happens. So I need to say this little delta, well, that will be a half. If I happen to have a situation here where I've fed in an epsilon which is less than 1 over 100, then this whole part here is going to be at least like 0.49 to the power 5 times m. And you saw over here we factored it out. So what I was trying to emphasize is this is like a constant fraction of the cluster. And in fact, if I look at what constant fraction it is, if I happen to be in this regime where I chose to make, if I was given the delta equals 5 and I chose the epsilon to be less than 1 over 100, well, then this whole quantity here looks to me like it's going to be at least something like at least 0.49 to the power 5 minus 5 over 100. That sounds bad. 0.49 to the power 5 sounds too small already if I'm going to take 5 times 1 over 100. So that's suggesting to me, okay, this thing makes the top inequality work. If I want to make the bottom inequality work, let's just put another 0 on here. So now I'm going to say, let's just go and choose epsilon to be, I'm going to use any epsilon which is up to 1 over 1,000. And if I put that here, now I have something interesting. Because if I put that here, the delta is 1/2. 1/2 minus this tiny, tiny epsilon is pretty close to 0.4, it's at least 0.499 to the power 5. Minus 5 over 1,000. Is that big enough? I think that's a positive number. So 0.499 to the power 5 is going to be at least around 1 over 33-ish, I think, because half to the power 5 is 1 over 32. So this will be at least like 1 over 33 minus 5 over 1,000. 5 over 1,000 is like 1 over 200. Excellent. If I do that, then what do I get? If I make this choice, then what I get here is I get this. It's going to be at least 1 over 1,000. This part's going to be at least 1 over 1,000, the square bracket, and then times m. But why I'm so excited is that I got a bound which is at least a constant times my cluster size of m. So now I want to put into a new screen what we've just said. What we've just said is if the little delta is 1/2, and if the big delta is 5, then by choosing any epsilon, which is less than 1 over 1,000, I can do something pretty interesting. I can find any graph that I want inside. It doesn't even have to be like 3 clusters. It's like inside any old regularity diagram, I can find any graph as long as that graph has maximum degree at most 5, and that graph is allowed to eat up at least 1 over 1,000 of every one of the clusters. This is amazing. Let me write that down now. So what we've just proved. In any regularity diagram, where the regularity diagram is going to look something like this. It'll have a bunch of clusters, and it doesn't have to have only 3, doesn't have to have only 4. It could have a large number of clusters, but it'll be a constant number of clusters. But whatever we write down is going to be a statement that doesn't even care how many clusters we wrote. With a regularity diagram, each cluster has size m. Okay, and in this particular regularity diagram, I'm going to be a bit more specific. I'm going to say that there are some pairs of clusters which are interesting. Not all, but some. Maybe like this. I just drew something like this, where the blue lines mean some pairs of clusters have density bigger or equal 1/2, and they're epsilon regular. I'll make that epsilon a bit more readable. So I'm given this situation. Some pairs of the clusters, density at least 1/2, and those pairs are epsilon regular. And so in any such thing, I'm going to say that if I have some graph that I want to put inside this, in any regularity diagram, given any graph, of maximum degree at most delta, which my delta is 5, my capital delta, maximum degree at most my capital delta, which is 5, inside this regularity diagram, given any such graph of this, where that graph also uses up at most 1/1000 of the vertices in each cluster, okay, any graph of maximum degree this, which can be, I'll call it be embedded in, let's call it the blown up version of this graph, where all of those blue lines are replaced by complete bipartite graphs. Let's call it the blown up version. Well, I shouldn't call it blown up. We're not really blowing up anything. Well, I guess it is. It's sort of like blown up. This is like a diagram. This looks like a graph, but you should think of this as m vertices, m vertices. Every blue thing is a complete bipartite graph. So let's call it the blown up version. Of the regularity diagram, where each blue edge is replaced by a complete bipartite graph is actually inside the original graph. So I'm saying that given any graph that I could embed inside this thing is actually inside the original graph. Is actually inside the original graph. There are some conditions, of course. We're going to write down some conditions. Inside the original graph. And the conditions are as long as. What do I need? So again, what I've written down is something quite impressive. It's that, before we were looking for like two disjoint triangles, and we were going to put the two disjoint triangles maybe like here and also somewhere like here. But now we can actually go and throw anything we want. We can throw any big graph that we might want to put into here, as long as that big graph happens to have its edges falling inside only the areas that I've marked with the blue. I actually made it a little bit stronger than what we had before. What we had before was they were all blue. So they were all epsilon regular and all density at least half. But here, all I need is that I can put them inside here as long as, so over here I said that the maximum degree is at most delta already. So the only thing I need here is as long as the graph uses at most m/1000 vertices of each cluster. As long as we use at most m/1000 vertices per cluster. And there's one more condition here on the epsilon regular. I actually will need that it is epsilon regular with like 1000 as my choice of epsilon. So I'm actually going to go and take this epsilon, I'll replace the epsilon, and I'll say, we can use a very specific epsilon. With epsilon equals 1,000. I'm going to pause here and ask, are there any questions? Or rather, does this make sense? Or did I miss a condition? I think there's so much that has happened so far that I think we need to maybe pause and take a look at this. So where did this come from? Where this came from was that originally I did something where every single pair was density at least the delta, which is half, the little delta, which is a half, and also every single pair was epsilon regular. Now, what we ended up doing is we ended up trying to find out under what conditions can you put some bigger graph inside, as long as I enforce that the bigger graph has a bounded maximum degree. And so if that capital delta is 5, then in fact my conditions on when I can find the graph inside, where I'm putting some vertices in here, some vertices in there, some vertices in the top cluster, and so on, my conditions get satisfied as soon as, since I have my little delta being half, and since I have my big delta being 5, those are satisfied as soon as I use epsilon to be 1,000. Let me go back to the calculation. The calculation was here, and I said, as long as I choose epsilon to be less than 1,000, well, then this is at least 1,000. I should emphasize that this 1,000 for the lower bound and this 1,000 for the epsilon do not have to be the same number. If, for example, I chose to make this epsilon here 1 over 10,000, over here, I would still write bigger 1 over 1,000 if I felt like it. I'm just emphasizing that my conditions are, as long as I put a ceiling on my epsilon, I will get a floor on this piece, and this upper inequality is guaranteed to be true. Okay, I'm going to pause for questions. Liam is waving. Do you have something to ask, or you're welcome to to ask? So you're asking, like, suppose I don't want. I think I'm trying to understand your question. So in the question you have asked, we're basically, in this drawing I've drawn, we're looking to embed a graph which you could imagine putting the graph in 4 parts, and you want to put some vertices here, some vertices there, some vertices there, some vertices there. Your question sounds like you're wondering, what happens if the graph I'm trying to embed, maybe it's like 3-partite with like one more part with just one vertex? And you're asking, is there maybe something better you can do? The answer. So another way to think of this is, like, what if the graph you're trying to embed? Yes, I see. So another way you can phrase this is you could say, well, I could also just try to put down some graph where each vertex is its own part. Now, that you could do, but I'll say that the most useful part of the regularity lemma is when you go and say, I want to start to bring my vertices together. I want to start to have, like, multiple vertices that I put into the same cluster. And the reason is because if you put vertices on their own parts, like into different clusters, you actually don't get any gain from the regularity lemma. I don't know if that makes sense. I think that's why I wanted to dwell on this picture for a while, because this picture is amazing. This picture is saying, as long as I have epsilon regularity with like 1 over 1,000, and if my densities are all bigger than half, then it doesn't even matter that these are not complete. What I'm saying in this theorem is amazing. It's saying, just go and make them complete bipartite graphs, and you can find anything you want in there. So this is actually quite shocking. The idea that I could go and put all of the edges I want between these pairs of parts, and as long as when I finally look for my graph doesn't use more than 1 over 1,000 of each piece, it's there. Did that make some sense? So the goal here.
Yeah, I sort of get it now.
Yes, because the question you asked is legit. I mean, you could, for example, just go and say, yeah, I can go and look for something which is 1 vertex per part. But in some sense, then you'd almost be playing the game of Turan's theorem. The idea here is that in the same way that the Erdős-Stone-Simonovitz theorem was able to prove something like Turan's theorem, but for chromatic number instead, is exactly what this is about. The reason chromatic number arises is because chromatic number is talking about, like, how many parts you need in order to stuff your vertices of your graph, classify them into these different parts. So that's actually why I really wanted to dwell on this slide, because until here you don't really see the huge value of the regularity lemma. But here you see something that feels really too good to be true. Because a complete bipartite graph, that's like everything. And somehow you can go and find it inside here. Any other questions while we're on this screen? Because then we will start to use this. Okay, so now let's go and see what we can do with this. So this is some very powerful thing, and somehow we're doing it with 1/2. I do want to emphasize, if you wanted different values, if you didn't want 1/2, if you wanted 1/4, and if your delta, your capital delta was 500, you could go and work out some new bound on the epsilon. The only reason I did this all with real normal numbers is just to show the exercise of what you do. So given any lowercase delta, any uppercase delta, there is some bound on your lowercase epsilon, which gives you another constant here to put so that you get at least constant times epsilon fraction per part. Okay, so now let me go into what we're actually trying to do, what we're actually trying to achieve with this. We're trying to prove a Ramsey number problem. So what do I mean by Ramsey number problem? So let's review. So definition. The Ramsey number, and we're going to do something about graph Ramsey theory, Ramsey number of H is equal to the minimum number of vertices, n, such that if you have any two coloring of the edges, two coloring of edges of Kn has a monochromatic H. Okay, and monochromatic here means that every single edge is the same color. Now, we already know that this R of H exists. We, for example, have an upper bound. From what we had before, we can call this an observation. Can anyone tell me an upper bound on the Ramsey number of H? It's finite. Can someone tell me some bound? It's just some finite number. Feel free to raise your hand, or actually, if you open your camera, you are also welcome to just like wave, because I can see everyone there. Or you can use the yellow thing. Either thing is fine. I want an upper bound. Asymptotic is okay. So what's a bound on number of vertices? So that, yes, I see Bryce. Hi Bryce. Are you raising your hand? Yes, you can use 4 to the power, I'll call it V of H, which is the number of vertices in H. Because of course I could just say, well, let's just go look for a complete graph with that many vertices. Yeah, I mean, that's what you meant. I mean, this n here is just a different n. But the Ramsey number is 4 to the power number of vertices of H, because once I find a complete graph with the number of vertices of H, which is monochromatic, we're done. If you were wondering, this does not have to be an induced monochromatic H. In fact, otherwise this would be not a very useful concept. So this is by seeking complete graph with vertices of H, vertices. Now that's exponential in the number of vertices of H. It turns out that there's another interesting bound that you could try to study. We could try to find out what's the Ramsey number of graphs which have maximum degree at most 5, or maximum degree at most delta in general. So here's a natural question. Suppose you're given delta, capital delta. Now what I want to do is I want to find a number which is it's determined by the delta. I guess I should call it, what should I call it? I guess I can call it R delta. I'm not going to do a parentheses. I'm just going to call it R sub delta. It's like a Ramsey number, such that every graph with maximum degree delta has Ramsey number. Oh, actually, I shouldn't have called it R delta. I want a function. It's not a number. It's R of n and delta. N is the number of vertices. Delta is the maximum degree. Okay? And in fact, this is also where I'm seeing Bryce had said n, and I just said n. I don't want n. I want t. Okay? So I'm going to erase this R sub delta. Let's just call it... I guess I'll reuse R. R of n and delta, such that every graph with maximum degree delta has the Ramsey number of the graph being less than this R of n and the capital delta, t. Oh no, I screwed up again. This is a t vertex graph, okay? Such that every t vertex graph with maximum degree delta has the Ramsey number at most r t comma delta. So effectively what I'm trying to do is I'm trying to say up here, I have something which is 4 to the power t. It's exponential in t. Can you do any better if you know something about the maximum degree? For example, if I have t vertices for my graph h, and my maximum degree is at most delta, could I do any better? And the motivation for why you might expect to do better is, for example, if I said the maximum degree is 1, I can prove pretty good Ramsey numbers. So just as an example, suppose I'm thinking about the case where my h has maximum degree 1. Then what's h? H is just a bunch of isolated edges. And in fact, the Ramsey number of a t-edge matching you can show is linear in t. So let's start with another observation. That one I'll just give as a, if you're curious, you can play with that. That's not a very hard problem to do. Observation. If capital delta equals 1, then h is a matching. Not a perfect matching. I'm just saying it's a matching, which looks something like this. And it's well known that if you have a matching here with, let's say, t vertices, okay? So I'll just say there's a easy exercise, which is that the Ramsey number of a t vertex matching is at most some constant times t. It's linear in t. I'm just going to put down 100. But you can do better than that. So it's like there's actually some number you can write here, and there's no need to get more than a linear number of vertices. If you're going to color all of the edges, you're going to, for sure, find one of these monochromatic matchings with size at least t vertices. And the 100 is not the important number. The important thing is it's somehow linear. This is linear in t. And then it became interesting to say, well, if I have other fixed deltas, fixed capital deltas, fixed up capital deltas in front, can I prove other bounds? Obviously, if I let my capital delta grow as my graph h grows, I cannot. Because, for example, if I went and said, here's a graph, it's a 70 vertex graph, and its maximum degree is 69. Well, that's called K70, and there's nothing else I can do. That's going to be at least root 2 to the 70, as we know from the lower bound on Ramsey numbers. So that's useless. On the other hand, the question that's interesting is, suppose you just fix that 69 for the maximum degree. And then now you let the number of vertices t just keep growing. Well, it turns out there's a beautiful theorem. And in fact, I want to see if I can maybe even... Okay, yes, I have a little bit of trouble sometimes remembering things like the names. The reason is because in my head it's all about the math and the reasons, but names are also important. These are the names of the people behind the following theorem. So let me write down. This is a theorem with 4 names: Quatal, Rodel, Semeredi, and Trotter. So there's a theorem here. It's by Quatal. I also want to make sure all of the accents are in the right place. Quatal, Rodel, this is a 2 dots on the O, Semeredi, and Trotter, no accents. So Quatal, Rodel, Semeredi, and Trotter proved that if you're given any maximum degree, then there is some constant that depends on the degree, which is your linearity constant. And the Ramsey number of t vertex graphs with that maximum degree is actually linear in t. So what this says is, for any maximum degree delta, there exists a constant such that the Ramsey number of h is, well, let me put a for all in front. For all graphs h with maximum degree at most delta, I have that the Ramsey number of h is actually less than the constant times the number of vertices of h. This is amazing. So this thing generalizes what we had before. So this thing generalizes what we had before. What we had before was something which was just, if my maximum degree capital delta was 1, then there's a constant c. I don't know, like 100 will work. So that the Ramsey number of any graph, which has some t many vertices, but has maximum degree 1, has Ramsey number at most 100 times t. And this is just saying for different values of the capital delta, you get bigger values of c. And then that's just the multiplicative constant with the number of vertices. Amazing. Okay, so now we have to prove this. And the claim is that the idea is that the proof of this just depends on what we were just doing. What does that have to do with the regularity lemma? And what does that have to do with capital delta being half? Some of these ideas already came out last time. So I'm just leaving this here so we can kind of dwell on what we're doing. We're trying to find a monochromatic object, and we have 2 colors. What do you think the half has to do with the 2? We're going to do the proof, but I want to let people kind of say some stuff. Like I went through all this effort to say like half, 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 and I have 2 colors. And I have these kind of notions like I can make these kinds of objects. Does anyone have some idea of things that we might use? This is something which you now are equipped with a lot of the tools that will crack this. In fact, the answer is that we're going to almost have 2 different regularity diagrams. And the idea that somehow you might have missing stuff, that is true. You might have missing stuff. Well, maybe we should make a new regularity diagram. So I'm going to say, with all of this, I now know that if I had my capital delta being 5, I'm going to end up doing something with maybe epsilon equal 1 over 1,000, maybe, or maybe even less. We might do even less, okay? But let's go and move into what we might try to draw. Proof. So I'm going to apply the regularity lemma because, by the way, this is the last thing we're doing on the regularity lemma section of this entire class. So we should finish it with an application of the regularity lemma. We're going to say, let epsilon equal something. And that something is going to be determined by capital delta. This is going to be depends only on my capital delta. Because that was the only ingredient. The only input to the whole theorem was a capital delta. Now we're going to apply regularity lemma. Semeredi's regularity lemma, and what I get is I get some diagram. It's not a regularity diagram yet, but I have this object, and what I have is I have T clusters. Yes, all of them are almost the same size, up to like plus minus 1. Let's just call them all of size n over t. Plus minus 1 is not going to matter in this. All of size n over t. And we know some conditions. What do we know about the t? Can we review? What do we know about this t? We have some bounds on this t. Feel free to raise your hand or wave or something. Two bounds. Both of them are important. Yes, Matthew. No. Okay, Anthony. Oh, Matthew. Say again. Ah, okay. So it looks like the latency went. Okay, that's totally fine. Anthony, did you want to say? Yes. So we know that there's going to be at least 1 over epsilon, so there'll be enough clusters. And we also know upper bound. It's at most some m, right? And the m is a function of epsilon. So what we have is this epsilon is what came in from this capital delta, and the Semeredi regularity lemma is going to give me an m. And m is just a finite number, some number, okay? And then now I have this regularity diagram, except that in this regularity diagram, sorry, it's not a regularity diagram yet, this is a partition. And what I know about the partition is that almost all pairs are epsilon regular. All but less than epsilon t squared pairs are epsilon regular. Okay. So that's nice. Almost all of the pairs are epsilon regular. now I claim we want to do something with the 1/2 and with the fact that almost all the pairs are epsilon regular. So maybe let's now try to draw a regularity diagram, but let's draw a two-colored regularity diagram. We have two colors, blue and red. Some edges we'll draw in blue. Some edges we'll draw in red. That doesn't look red. Some edges we'll draw in red. And some edges are not drawn at all. Why? Well, if I look at this, the edges which are drawn in blue, those are going to signify epsilon regular pair and blue density at least 1/2. So something that's very important is that if you have an epsilon regular pair, I should have said what we're doing. How do you apply similarity regularity lemma to a complete graph? That doesn't make any sense. Maybe that's why everyone stopped. So, right. So I'm letting epsilon equals this. What am I given? I'm given a two-edge coloring of Kn. So let's start with that. So we're given a two coloring of edges of Kn. Now, what am I going to apply similarity regularity lemma to? I have to apply it to a graph, and I can't apply it to Kn. That would be boring. I'm going to apply similarity regularity lemma to the graph of blue edges. Now that's a graph. That's an n-vertex graph. So let me write that down. Apply similarity regularity lemma to the blue edge graph. So now that still is going to be n-vertex graph. But there's a reason this is exciting. The reason it's exciting is because the red edge graph is the complement. Liam, yes, I see you have a hand.
Yeah, just for bookkeeping, we're picking small delta as a 1/2 here, right?
We are going to pick small delta equal to 1/2 here. That is correct. But I didn't even need the small delta yet. The small delta equals 1/2 is about to drop out of how I'm coloring these edges. Coloring the edges in this diagram that I'm drawing. Okay? So the point is, I've applied similarity regularity lemma to the blue edge graph. But there's a key observation. Maybe because I did this, all but these many pairs are epsilon regular, this is true. Let me put another very key observation over here on the right. I'll use the red. Even though we applied similarity regularity lemma on the blue edge graph, since the red and the blue are complementary, meaning I started with a complete graph, so whatever is not blue is red. Since this is true, every blue let me not write every blue. I want to say epsilon regularity for blue edges implies epsilon regularity for red edges also. So since this is since these are complementary, given any vertex pair, let's call it blue epsilon regularity, is true if and only if I have red epsilon regularity. This is a crucial item. And the reason this is true is because if I have two disjoint sets of vertices, how does the blue density and the red density compare? Well, they're related. They add up to 1, for sure, because every edge is either blue or red. And because of the fact that you can write down red edge density is just 1 minus blue edge density, then all of the things we had defining epsilon regularity, like epsilon regularity was for every subset of vertices of size at least epsilon fraction. Well, that's still okay. Then I need that the density of, say, red edges between those two is close to the density of red edges between the whole thing. Well, of course, they're just 1 minus the blue densities, and it was epsilon regular for blue to begin with. So now I can actually say what this picture is. Here what I've done is between any pair of parts of clusters, which is epsilon regular, I'll draw an edge. And I'll make the edge either red or blue based on whether the density between those two parts is blue at least half or red at least half. If it's equal to half, who cares? Just like whatever. Okay? This is amazing. So this trick is amazing. It's like, what? Okay, Anthony, yes. That's a great question. What's the point of applying similarity regularity lemma to the blue edge graph if the red one is going to be as epsilon regular as the blue one? The answer is there's nothing special about choosing to apply regularity lemma to blue. I could have done the same thing at the very beginning where I say apply similarity regularity lemma to the red edge graph. But what I could not do is apply similarity regularity lemma to the union of red and blue graph because that's just Kn. So the point is that we have now gotten like a colored version of the similarity regularity lemma where I get to draw these lines and one line between two parts indicates something very powerful. The line between two parts indicates that it's epsilon regular pair and that the density, the blue density, because it's in blue, is at least a half. And the same thing is true of this pink thing. The pink thing, or red thing, is just same, but red density. Okay, so now we're in amazing shape because we now have these regularity diagrams starting to materialize and the density bounds of this lowercase delta are half. So I got that already. So now what am I trying to do? I'm trying to do a Ramsey problem. I'm trying to find this h. What do I know about h? So with h here, I know that h has a certain maximum degree. That's very handy. But the maximum degree alone is not enough because as Liam had asked, like if I try to embed every vertex of h where I put one vertex into each part, that's not super useful. However, there is one kind of structure which if I could find would make me really happy. And that would be in the regularity diagram, if I had the chromatic number of h many clusters linked all together in a complete diagram. Let me draw it on the next screen. Here is something that would be great. It would be if I had some clusters. Remember, all the clusters have size the same. And in these clusters, I happen to have blue, 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 blue. And the number of clusters inside this picture is like out of the T clusters, suppose I got chromatic number of H many clusters. Suppose I got that out of the T. So this is like out of all T. There are T many clusters. Suppose I got that. Now, if the clusters are just big enough, I would be in good shape. So I would like to have chromatic number of H many clusters, and each cluster size. What do I need now? Well, what I need is that each cluster size is going to be at least some constant depending on the delta. So I'm already going to have one constant here. Some constant, C delta, constant depending on delta, times the number of vertices of H. Now, where does this C delta come from? This C delta is 1000 if delta equals 5. So we did an explicit example earlier where if I had the delta equal 5, let's think of the example. If the capital delta was 5, C delta equal 1000 works. Do you see why? It's because if I see this particular picture here, the previous thing we proved would say, now I've got this graph H. And my graph H, I can think of it as having chromatic number. So, it has a chromatic number. So I would put the vertices of H in those different clusters corresponding to the vertices, the different color classes of H. And because I'm able to find H, as long as I use less than 1/1000 fraction of each cluster, I'm done. I'm going to pause here. Does this statement make sense with the delta equals 5 and the C delta equals 1000? This thing here, we would actually, sorry, I need one more thing. Inside this, I would also need that the epsilon that we used was less than 1000. So it would be great if this delta equals 5 and if we used and epsilon, which is less than 1 over 1,000. Then I'll be in good shape. But that's okay, because I can enforce that since I have an epsilon equals blank. So I can choose a very small epsilon to begin with. So that would be great. By the way, let's use another bound. If I need to have chromatic number of H, that's another quantity to throw inside. I want to erase chromatic number of H and replace that with something simpler. It is true that chromatic number of H will let me get done. Does anyone know another quantity I can write there that also gives me this happy conclusion? What's a bound on chromatic number of H? What are we given at the beginning? This whole statement starts with a capital delta. So I have a bound on chromatic number of H. It's delta plus 1. So in fact, if I had capital delta plus 1, many clusters, such that all of these blue densities between them are at least all at least half. And if I just make sure that the clusters are big enough so that they're big enough to put all of the vertices of H, I'll be in good shape. This should make you feel somewhat happy, because the bound on the size of the clusters we're getting is a constant, like 1,000 times the number of vertices of H. And in the regularity lemma, the size of the clusters is also linear in the number of vertices. The number of vertices compared to the size of the cluster is related by this capital M. So let's also recall, each cluster size is always at least n over t, and the bound on t was m. So I now know that there's some m, and the m only depends on delta also. M is only depends on capital delta. Let me write that more neatly. Only depends on capital delta. That's your m. So if you tie all this together, this is starting to give you a linear bound. So if only I could find this kind of an object, I'd be in really good shape. If I could find this kind of a complete capital delta plus 1 partite graph, I actually will just know that as long as my little n is bigger than m times c delta times number of vertices, I'm good. I'm just tying all of these together now. So if I combine all of these two things I have here, what I get is then n bigger equal capital M times c delta times v of h gives the blue h. Are people following? Are people following here? This is like, it's like magic, but it's most fun if the magic gets opened up. So again, what I'm saying is I would love to find that. I would love to find a complete blue object in my regularity diagram. And my complete blue object only needs to have capital delta plus 1 parts. Think of capital delta as 5. It just needs to have 6 parts. All I need is a 6-part thing. Anthony, I see you have a hand. Thanks for asking. Are n and the number of vertices in H the same thing? No. The number of vertices in H, I'm intentionally suppressing. I called that T. N here is we're trying to find out that if my little n is big enough, I want to know that there's a monochromatic H. So the goal of Ramsey theory is to say, I look for monochromatic H. I need to show that as long as my little n is bigger than something, I get my monochromatic H. So what I'm doing here is I'm going to say I'm given a 2-coloring of the edges of some kn. I will eventually at the end find out that as long as my little n was at least a constant times the number of vertices of H, boom, I have my monochromatic H. Right? So that's the flow of logic here. We need to show that capital delta is given. Maybe it's 5. Oh, Anthony, you have another question.
On this slide where we have
Oh, size v of h over t. No, actually, thanks for asking. My n here is the n which corresponds to the kn that we have a 2 coloring of. I'm being very careful that wherever I have the number of vertices of h, I'm writing it as v parentheses h. So the flow is capital delta came first. That's the maximum degree bound. Then came a graph, h, which has maximum degree delta, at most delta, but it could have a ton of vertices. I don't know how many vertices it has. It has v of h vertices, could be unbounded compared to what I had before. Then my goal is to show that as long as my little n is big enough, I want to show that as long as my little n is big enough, in fact, the bound is about to show up here, as long as my little n is big enough, bigger than m times c delta, times the number of vertices of h, then immediately I would get a monochromatic h. Because this is a Ramsey number upper bound. So I'm trying to show that when I have enough vertices, then every 2 coloring gives me a monochromatic h. Thank you for asking. There are too many variables flying around, so those questions are very helpful. So I'm now saying, if only I got that monochromatic, that blue, actually it could be monochromatic, it could be red or it could be blue, but like something which has all of these pairs with density at least half. Well, we got that because that's how we drew. Liam, you have a question.
So aren't we going to need to do some sort of Ramsey on the T clusters, treating them individually as vertices? And doesn't that sort of break everything because then we have to do Ramsey again?
Okay, thanks. You're saying, but we need to maybe do another Ramsey because we have somehow, we don't know whether we'll get to have this capital delta plus 1 blue clique or a capital delta plus 1 red clique. Remember, think of this as capital delta is 5. So I'm looking for like a blue K6 in this diagram or a red K6 in the diagram. So you're right, we have to do a few more steps. But I'm just showing that if I had this, I'm in great shape. So suppose I found this thing, then as long as my number of vertices was at least this m, and the m spat out of the capital delta, the m spat out of the epsilon, right? The m spat out of the epsilon, and the epsilon is going to be something that depends on the capital delta. So all of this stuff depends on capital delta times vertices of h. That's just a linear bound, meaning that as soon as my n gets beyond 50 million times number of vertices, bam, it would be there. And this Ramsey number, I'm just trying to show that I can put a constant here in front of the VH. But now Liam has said, wait, I don't know if I can get that. I might actually have to deal with a red one instead. So we'll do another Ramsey. So it would be great if we could get this, but we can't necessarily get that yet. Here's something else that would be great to get. Would be great if I could at least get some thing like this, which is now much bigger. It's not K6. In fact, the number of vertices, the number of clusters here, the number of clusters is another Ramsey. It's the Ramsey number of delta plus 1, delta plus 1. What I mean is it's enough clusters so that if I have something where every single edge is either red or blue, I should have drawn less, but I hope that's all of them. No, that's not all of them. I'm just trying to emphasize that everything is here. Would be great to get something like this. It's in the regularity diagram now. The number of clusters is, r delta plus 1, which it's bounded. It's some number. Okay, it's some number depending on delta, no bigger than 4 to the delta. Would be great if I could find something like this. Inside, would be great to see this in the regularity diagram. Why? Because if I found this thing in the regularity diagram, what does that mean? If I found this thing in the regularity diagram, let's go back. That's this object. It's going to have this object for sure because of Ramsey, because what Liam observed. If I just get this many clusters to be a all complete, but with 2 different colors, then as long as I have n being bigger than m times c delta times vertices, bam, I've got an h. So let me write down the conclusion here. That's important. Because then what I get is then any n which is bigger equal m times my C delta times the vertices of H gives a monochromatic H. I hear a microphone. Does that mean someone has a question? I'm happy to take that. If not, maybe I'll just keep going, right? So I need to have this. If I have this, I'm all done. Well, when I say if I have this and I also have n big enough, I'm all done. So now how could I get this? Well, what does this mean? What this means is that every pair here of clusters is epsilon regular. Actually, that's all it means. I mean, all I need is that every pair is epsilon regular, because then it'll either be red or blue. So now, how could I find that? This is where Turan's theorem comes in. This problem uses both Ramsey's theorem, and Turan's theorem, and the similarity regularity lemma. You see, if I go back to the original picture of this partition looks like this. And the similarity regularity lemma says that all but epsilon t squared pairs are epsilon regular. Now what I'm looking for is, I'm just going to look at this like zoomed out version. I want to find a complete graph K Ramsey delta plus 1, delta plus 1. I want to find a gigantic complete graph inside this red-blue, as these red-blue edges. But now, I already know that almost all the pairs are epsilon regular. And so if I look at this, and I just draw another graph where I just draw one vertex for each one, let's do this. So the regularity partition, the similarity regularity lemma partition, it looked like this. You had t parts, but these parts are just vertices now. Okay? So I had t parts. And those I think of each as one vertex. If I've got that, now I'm going to go and look at what happens with some of these pairs. I'm using green now to say that some of these pairs, well, all but at most epsilon t squared of the edges, I'm going to use the word super just to emphasize they're not normal edges, are there. Does that make sense? I've got this picture now. It had t vertices, t super vertices, and it's almost a complete graph. All but at most epsilon t squared of those super edges are there. And so now here's the point. If epsilon is small enough, let me just write small enough, there's a k Ramsey number delta plus 1, delta plus 1. Does that make sense? And actually, what does it mean if epsilon is small enough? If I was looking for a k4, just to remember where these bounds came from, if I'm looking for a k3, I just need epsilon to be, at most, I don't know, like the maximum number of edges in a k3 free graph is t squared over 4. Okay, let me write down a few of those calculations. Okay, so let's recall. The maximum number of edges in, let's say, a t vertex, k, let's call it r, free graph, is the maximum number of edges that you could get is if I put the t vertices. Now these clusters are not the regularity clusters, but I will make a bunch of these things. I'll make r minus 1 clusters. We do this. I guess once I start something, I feel sort of like finishing it. I hope that's right. I've got this many. And how many edges are here? The number of edges here is about 1 minus 1 over r minus 1 times t squared over 2. We're going to use Turan's theorem right now. This is Turan's theorem. So what it's saying is that the most number of edges anyway I could find to avoid the k r delta plus 1 is 1 minus some other constant right here times n squared, times this t squared over 2. So in particular, this is like saying the number of missing edges is at most a constant times t squared. That's what this is over here. We're about to finish this lecture. This one is a long lecture because I just want to include the whole proof. But this thing here is what I could use. I could compare my epsilon to this. It's just like, just make your epsilon small enough so that you are beyond this. So make your epsilon smaller than this. Pick epsilon smaller than, well, this. And since I said this, I'm going to draw a different box because it's epsilon t squared. Okay, so let's now look at how this whole thing fits together. Let's look at how this whole thing fits together. I have now an important thing on epsilon. How small should epsilon be? It's not this 1 over 1,000 anymore. In fact, I'm going to have to look at what this r is. This little r is that I want to know what kind of Turan number or how many edges I can afford to lose. And like if I only lose that few number of edges, then automatically there's a k like 4 to the power delta. That's what I want to find. So I'm looking for a k 4 to the power delta in my green diagram. If I want to get a k 4 to the power delta, then I need to choose my epsilon to be something like 2 times 4 to the power delta. 1 over 2 times 4 to the power delta. That's pretty small. Okay, so my epsilon is going to be pretty small. When I look at this thing, I'm saying there's a delta given, so I'll choose they'll give me a bound on r, which is like 4 to the delta. And then so a bound on epsilon is, I'll choose an epsilon, which is around, let's put it in the blank. Epsilon is going to be around this something like 1 over 2 times 4 to the power delta. Something like that. It's not exactly this. I mean, maybe I'll even put the plus 1. Then it might actually be exactly this. But I'm putting this epsilon here because what does that achieve? If I put that epsilon there, then I can look at this particular diagram that you get from the regularity lemma. On this diagram that you get from the regularity lemma, you now know that all but epsilon t squared of those pairs are epsilon regular. At that point, that tells you that if I went and zoomed out, if I zoom out like this, then I have some t many super vertices, and only at most epsilon fraction of those super vertices are like not epsilon regular. But now I chose my epsilon small enough that this is in fact beyond the Turan number of a k, beyond the Turan number of a k r plus 1, k delta plus 1. Since I'm beyond that Turan number of a k delta plus 1, a k Ramsey number delta plus 1, then there's going to be a picture like this. And in this particular picture, I happen to have Ramsey number, at least Ramsey number delta plus 1, many clusters, and every single pair between them is epsilon regular. Since every pair between them is epsilon regular, you now use Ramsey's theorem. Ramsey's theorem tells you that even though you had, well, because you had Ramsey number delta plus 1 blobs, that gives you automatically delta plus 1 blobs, where it's now monochromatic. And now that you have these delta plus 1 blobs which are monochromatic, the thing which we had done with the lemma from last time tells you that the number of, as long as your n here, the original n, was big enough, then you would be able to find your h in there. And what condition do you need on that n? Your n just has to be at least the c delta times this capital M. The capital M came from the epsilon. The epsilon was pretty small. The epsilon was 1 over 4 to the power delta-ish. The capital M is a tower of 2's of height, like 1 over 4 to the delta, to the power 5 or something. And so ultimately I get a bound here in front, where the only thing it depends on is delta. This M times C delta only depends on delta. It's kind of huge. It's like some huge number. If delta was 5, this is already beyond belief. But it's a huge number times the number of vertices. And that's it. And then it works. So this actually gives the entire monochromatic H. And the only thing you needed was to have number of vertices to be at least linear times the number of vertices of H. Okay, so that finishes this class. I know this one went over time. But I have a question. Does anyone have any questions? I'm happy to walk back through some of these if this thing was slightly confusing. This is the particular lesson that I wanted to end the regularity lemma section with, because this is the one that uses everything. Oh yes, Bryce, yes? I'm sorry, could you please say that one more time? You said C delta? Yes, how is C delta found? So the way this C delta is found is that we were going to be good as long as we knew that each cluster size was at least C delta times the number of vertices of H. But where did that come from? That one came from what we did at the beginning of the class. It came from here. So in the beginning of the class, what we saw was that given that the little delta was 1/2, that gave me an explicit thing I can use. From the little delta being 1/2, I gave an example if the capital delta was 5. If the capital delta is 5, then you're able to say that any epsilon which is less than 1/1000, if you put it into these two inequalities with the little delta 1/2 and the big delta 5, the first inequality is true, and the second inequality is at least 1/1000m. The C delta is the reciprocal of this 1/1000. So that the reason for that is because, you know, I can embed this thing as long as I use at most 1/1000 fraction of the vertices in the cluster. So going back to the picture, in this picture then, I'm in good shape as long as each cluster size has at least 1,000 times how many vertices I need to embed total. This is like ridiculously amazing, by the way. Like this is like all the different things that we have done in this entire section and even like in this course have all come together to do this. It's like we ended up using the regularity lemma to get the very core piece, which is inside here. As long as I can find this nice diagram which has delta plus 1 blobs, and each blob is of size at least a constant times v, we're in good shape. Zichao, you have a thumbs up. I think that might mean a question or a statement. Okay, thank you for asking why we apply Ramsey. Yes, if there's a blue edge between two clusters, you could imagine that it's also epsilon regular with the red. But the issue is that I need to have the little delta equals 1/2. If I don't have little delta being 1/2, then my problem is that my little delta could be very, very small. It could even be small compared to epsilon. So the issue is that over here, in order to get something interesting, the interesting part comes here, by the way. In this part, the only way to get 1/1000 is if the very first bit of it, which is the delta minus epsilon to the capital delta, I need that to be at least a constant depending on capital delta only. That's actually how you know that you need to use a constant lower bound on the little delta. Because if this little delta was allowed to get smaller, then what's going on in the little delta minus little epsilon to the capital delta, that will not give me a constant lower bound. Make sense? Yes. So that's actually where that comes from. Good question. Actually, every piece is necessary. Are there any more questions? If not, I'll say this was the end of the regularity lemma. The good thing is that YouTube keeps all the videos. So you can actually also go back and take a look at any particular part of this if you're interested. The bottom line is that this is a very exciting way to combine together regularity lemma, Ramsey's theorem, Turan's theorem. Everything fits together at the same time, and you get this ridiculous bound. Not ridiculous, like a ridiculously amazing bound, where you just can get a linear Ramsey number. Linear! Of course, the constant here is not that great. And there are other proofs that can go and get a better constant. But it's very interesting to be able to tie everything together like this. And that finishes all we're going to talk about the regularity lemma. See you guys all next time.